Okay. So we are working. Okay. So it looks like we're streaming now. Let's get this show on the road. Here's my lovely face. Oh, my hair. There we go. That's much better. Okay. Feel free to chat. So we're going to do a quick intro into Bitcoin mining. And this is going to be kind of a series, and we're going to try to look at implementing a Bitcoin mining on an RD FPGA, then maybe look at the Pink or an MP sock, and then finally maybe finish with like a Vertex Ultra Scale Plus implementation to see how we can get better and better hash rate. So, Bitcoin mining. So, a quick introduction to Bitcoin mining is that there are cryptocurrencies, not just Bitcoin, but cryptocurrencies that are proof of work cryptocurrencies. These proof of works require you to basically to test different encryption keys until you get a desired output. And their desired output is usually having so many zeros at the beginning of what happens when you encrypt with a specific key, the output of the encryption core. And sometimes there's easier difficulty or harder difficulty where they demand how many zeros are to be, or how many characters of that output need to be a specific value. And currently, like Bitcoin, it looks like 20 zeros or more. And let's see. We're going to go look at the GitHub page. I can go find it. Here we go. So this is a clone GitHub page. And so where does it talk about it in here? Not really. But I have a CPU test. It will load. So this fork I have does a CPU test. And what it's basically doing is it takes a SHA-256 and it takes where was the random number? We have a random init word in zeros, and we're digesting this. We're joining the results for X and results. So they're joining the things together. And if the hex results, if there are so many zeros, and zeros being defined up here, of hex values, which is each zero is going to be a certain amount of bits. So let's see how this works in action. I got a Python window right here with some. So we did the end time, ran CPU test. I'm running CPU test right now. It's taking forever. I upped the difficulty, and I was curious how long it takes. So as you can see here, the resulting hash is this value right here. And is that how many values it has? Or where the broken result is coming from? Let's look at the code. Grab the code real quick. We want to. So we have the code right here. We have the output right here. So the broken result. Oh, so it's just broken into words? That's all it is? Okay. So where's the answer, right? So we're doing a hash update. Init word plus notes. 0. Wonder we could add there because we have zeros and zeros. A U random. Okay. So let's drop this down to like 2, right? Does it super quick. Let's figure out what these values are. I am curious to, let's see if we print hex of the init word, what do we get? Okay, it's a list, I guess. So yeah, here's init word, a big large binary value. And then announce bin, we add that to here. So let's print S. This is probably going to be a lot of stuff to print. Yeah, that's what I thought. And so there's the zeros and this, and I assume we're just updating it based upon, we're just adding a different encryption or changing the last bit of the encryption until we can get something new. So like what they're doing is they're changing the values. Let's print a separation here. Let's start. And so this would be a result, and this would be next. Is the hex result here, or we can just put the result here. So we go from 97 98, and the result is where we're trying to get a 2 in front. +1. Yeah, I wish I knew. So let's see if we can figure out more about SHA 256, right? What is the nums? Okay, so that makes sense. So we're looking at announce is what we're changing. Okay, that's interesting. I'm using the SHA 256 algorithm on this website. I've tried coding it. Okay. So we can go ahead and remove this stuff. So the nonce is what they want. I wish I understood that a little bit more about how you control what you want. So that's how many iterations that took, that one took. And so that makes sense. So we have kind of the average, and that's the key, I guess, getting this to work. And if we do up to difficulty 3, this was 0.006 seconds, and we increase it, we have 0.09. So almost 10x increase in work. We do 4. Larger translations to add. Yeah, about 10x increase. Now let's try 5 was the original value, so this was much larger. Okay, so this is kind of the software version we'll be using to compare it to an FPGA version. And this series is a look at trying to get this inside an FPGA and to look at these values. I'm going to have to read up more about this terminology to understand. I thought you just put a random value in, but it seems to be doing an incrementing value. Yeah, maybe we'll let this run on 6, and I'll show you the hardware. And in my free time, I'll try to understand this a little bit better so that we can properly implement it in the FPGA. Like, do you have to increment properly? And I guess I just need to understand SHA-256 better with because this right here is kind of the packet, right? This is our block, and then we add our, and then this is the key we're adding to it at the end. Try to get an encryption out of it. Interesting. Open this block diagram. And we have the code for this guy. Okay. Up better. Okay. Let's see if the Python's still working a little bit. Much larger values. And okay, so the previous one right here took 0.8 seconds. Well, let's see what this takes. I should print the time between each of these. See if there's any better keys for this. I can get my head wrapped around so far. So I guess you just create a new Merkle root. Maybe this is the 256 bits. So where's the Merkle root in SHA-256, right? Echo open digest SHA. Hello world dot. Different hashes. Our coin bytes to identifier. Next, we reserve the order of these from beginning to little and concatenate these values. Calculates for the binary data. Convert this binary form on the output. And reverse the order to little to big Indian. Great job. We have the original value for Bitcoin. Okay, I'm gonna have to read up more about that. Is version plus previous block hash plus Merkle root plus time plus bits target plus nonce. This gets hashed twice. Which coin are we talking about? Okay, different ways to do it. So we're right now not going to worry too much about a specific coin protocol. We're going to look at performing high-speed hash rates. Going to have to figure this out. Okay, yeah, that'll probably be a good thing to read through. Okay, so this finished. No, this did not finish. Oh, is it still like... Sometimes this stuff gets annoying when it freezes. Properties. I think those are the things we want. I don't know. Okay, hopefully it's still executing something. I think that's what we wanted to be at. Okay, so let's look at the FPGA. So this FPGA design came with that GitHub I forked. And it's relatively a basic design. You have the microblaze. We have some EMC memory, Ethernet connection to send back and forth data. UART probably going to resend data over as well. Probably Ethernet. These are just some displays. But the biggest thing here is this minor coprocessor, which is doing SHA-256. So what we want to do is we want to take this design. We're going to transfer it to the RD35T. Let me look at the utilization. We should be able to put this on a 35T, right? Right. 16% utilization. Yeah, this design should probably barely fit on a 35T. Actually, let me just make sure real quick. Curious now. So let's look at the Artix product table. The Artix Ultra Plus coming out looks pretty interesting. Want this, right? Product table. So we want to compare the 35T to the 100T. Compare, right? So hard to look at those numbers. So about 33%. As long as these are below 33%, we're not worried about the I/O. We'll figure that out. We should be able to integrate this on a RD35T. But yeah, so Hunter. I guess my question is, why do you have to increment it? Can you just do a random value? or whatnot. I guess I'm just curious of why we have an incrementing value and we start from 0 and we move forward. I'm kind of curious to, because we have to start, like, why do we have to start at 0? Is it just to show you how many times you tried? Like, why is that important? Why do we care about that value? Because it looks like you need, like, you need to identify it. So yeah, we have different hashes, we have different attempts. But does it matter? Does this value actually matter? Does it have to be incremented correctly, or like every attempt, or are you just looking for a value that works? I guess that's my question. That's what I'm curious. But yeah, this provides some interesting information, especially when it says that your IP is included or your block value is included. Since your block is different from everyone else's, your hash will be different, which makes sense. Your Merkle root will change, which is part of because it says the extra known portion of the generation transaction is incremented. Where is that? Merkle tree. Okay. It's incrementing the nonce matter. Let's see. 256 mining or hashing. Yeah. I guess the best answer, it doesn't matter. Like, there's already so many things you can change that maybe it's more of just a statistic value than an actual real value. Yeah. Best answer, doesn't really matter. Okay, so that was interesting. So, this took 24 seconds. I must have froze it. But so we're going to run this at 6. Difficulty of 6 on our CPU and see what happens. It's probably going to take forever to run. And then we'll go look at the coprocessor on this FPGA design. So this is a very simple design, probably only getting shot to 56 once. And I know that we'll probably have to do it twice for Ethereum. Bitcoin, I think, is twice as well. I wish I got a little more detail. So we open up the code for this coprocessor, and it's probably a very simple thing. We have an axis and a master slave. Where are these axis and master slaves connected to? So the axis is to the microblaze, and the master is also to the microblaze. I've never really seen. Is it doing DMA? It must be doing DMA or something. Let's go look at this real quick. I can't look at it because it's locked. But I'm going to assume this is some type of DMA because it's axis stream. So we're DMAing information to the coprocessor. Get all those values, read enable, all words sent, validate, hash output. That's what we send through the slave interface. Okay, so it's going to be in one of those. This looks like the important thing. So our very basic interface, and we're just looking for data. And when the data is valid, we have an S counter, 20, zeros max, zeros T data. I wonder what S counter is. Enable. This is probably loading it, and the enable is somehow firing off, yeah, the SHA to 25.6. We have a hash input, which is a standard logic vector of the hash header. And basically, oh, he's using the counter to index into the header and apply the data. Okay, so that makes sense. And then we're enabling it. Minor management. Update if S is ready. Minor signals. So this is right here. And if hash length is this. So is this the hash length -1 down to the mask bits equals 0. I wonder if this is the difficulty. Yeah, that's probably the difficulty there. And so if it passes, we want the data out. Otherwise, we're going to increase this, update our original hash word. I wonder what happens if this goes greater than the 32-bit value. But it looks like we just add 1 to it. If output, so SPO ready, that means we're ready for the input. All words are sent, meaning, where is this coming from? This is coming from an input. That's from here. So we have all words sent, which is coming from the master interface. Yeah, that's right, Hunter. That's interesting there. We should be able to break that down pretty easily. And we'll have to look at the pipeline. This is what I'm curious about. I kind of want to break down the SHA-256 algorithm and how we can implement that into an FPGA, how we can pipeline it, how we can parallelize it, and how we can really take advantage of the different systems. I don't see an overflow on this, so that'd be interesting. What happens because we talked about the extra counts were in the header are in the Merkle root. Okay, so that's interesting. Let's figure out what this other interface is. So basically, I think this is just returning the correct hash value back to the microblaze. I've never seen this AXI port in a microblaze before. It'd be interesting to see how they do it. But yeah, so that's basically what we're doing. So let's break down into the SHA pipeline system. Oh, this is fun. This is definitely not optimized. We definitely can have a lot of fun optimizing this. Word array, that's interesting. Or do we have that defined somewhere? Okay, SHA functions. Here we go. We have a word array, 0 to 64, standard logic vector, that one. Hash array. Okay. The block, integer, range. So there's that parameter. Hash length is 256. Block is input message length plus input K calculator. Where's the K calculator? That has to be in here somewhere. Right here, K calculator. That must be added to the padding measure defined in some document. Return mod 512. Okay, so that's just padding with zeros. Pad with zeros, length 164, divided by 512, minus 1 down to 0, others. Okay, so we're just making an array of, that value. And we have some constants. See these values: init, ready, padded, scheduled, hashes. Reset, closing is what we enable. Enable is high. So we have interesting statements, right? Let's look at how we start off. So we want to do senable here, which enables the data. Update must be updating the value. So we must want to look at, do they have a default value? I guess they have a default value there. Oh, and they're using update to do the reset. So basically, as soon as enable goes high, we should be good. So if we go back here and ready, they must be using as an internal register, right? Because that's out. So yeah. Interesting. Sigma. This is going to be interesting. Initialize work. Or 0 else. Scheduled. This seems very, very simple. I have to play around, look at these other functions they have here. Message padding. Digest. Looks like it's just rearranging the words. Initialize. Constant hashes. Be interesting to look up. I'll look up this algorithm and see if these constant hashes and constant Ks are consistent for all implementations of the. I assume so. Update hashes. Okay. We can work with this. And then we can figure out how many hashes they do. Okay, so I'm sorry this hasn't been as interesting as I hoped it would be, but we kind of looked through this code. It's not very complicated. They have different functions that they're performing. And so our next step is that we want to just implement this system as is onto this FPGA, and then try to get their Ethernet system working and getting their software working with this device. Just see how their system is out of the box. And then we're going to have to spend another day breaking down the SHA-256 to understand how it works and maybe write our own pipeline implementation of it. Because I look at this and I see that the person who wrote this had a much more of a software background than a hardware background. So I definitely want to do this more of a kind of like how I would design as a hardware engineer and see how that changes things. So we're going to have to understand this algorithm a little bit better. and tried integrate FPGA design methods, I guess, breaking it down, parallelizing it, properly pipelining it, to hopefully be able to compute more than like one hash, to be actually compute multiple hashes in parallel. And maybe read a little bit more about the header and the Merkle root to figure out what data is coming into play. Microblaze is probably not doing much, but this is relatively a simple system. It's a good place to start. I'm glad I found this project. So we will adapt this for we'll adapt this system probably in a week or two. I'll have to look at it. But hopefully keep on with this, and we will eventually try to move this to larger FPGAs, more in parallel, and try to see how much we can improve the hash rate. And we'll probably want to do compute hash rate against like how many hashes can we get for a clock frequency? Because you know when we do dry stone as performance, there's a DMIPS per megahertz, and we should try to look at hash rate per megahertz. Like if I run this at 100 megahertz, what's the best hash rate you can get? And then maybe look at the power consumption at that 100 megahertz as well. So I wonder if the power consumption is linear. So we'll probably want to look and try to compute hash rate at a set frequency. What is the max frequency? What is the power consumption of that max frequency, to see what is a more efficient method. Because when you do Bitcoin mining, power is your cost and your hash is your benefit. And if we can be more efficient at slower clock speed, or be able to bump up our clock speed and get better results, we can improve our cost. So thank you for watching. Hopefully we'll be looking at some PCI drivers on Wednesday on a Vertex UltraScale Plus with Windows driver. So please join us